Okay, so good morning, and today we will continue our study of the Ising model, and we were pursuing an approximate computation which is called Weiss molecular field theory, or mean field theory, or we'll just call it mean field. It's also called the self-consistent approximation or method, because we don't decide. So what we said that m will be defined to be the expectation value of this thing, but m is left unfixed, and we got this equation which I'll write in a moment, where which we use to determine it. So at least it is self-consistent. Okay, so what we said is, if you go ahead and compute the expectation value of sigma I, that better be equal to m. So we did this computation and we got a formula, and the formula was m equal to one second. Yeah, so it was half tan hyperbolic, okay, of b plus the beta, I keep forgetting, beta times b plus j my. Okay, and I incorrectly said that y is a coordination number. I said we have to fix it, but I went back and checked. Y is equal to 1/2 of the coordination number. Okay, the reason is as follows. So if you go back to the Hamiltonian, that was minus j sigma I sigma j nearest neighbors minus b times summation over I sigma. Okay, so here, I mean, you just think about this thing. So this says that if you just suppose you think of each of these things at the vertices of the lattice, and draw a bond between nearest neighbors, so you can think of associating j with this bond. But in the summation, this will appear only once. But when I summed over I mean, we have to look at all the guys. So in a square lattice, there will be 4 bonds corresponding to the site I. Okay, but now when you sum over, look at the j summation, that will also pick this bond. So this bond, every bond is doubly counted. Okay, so y, okay, so this takes care of double counting. Okay, so the half in the definition of y, it's just a correction, I mentioned it yesterday, I wasn't thinking, only in words. In the definition of y is to take care of double counting. Okay, so I'll pause here and ask you for questions. Yeah. Yeah. Yeah, even yeah, that's a good question. I should have. I've absorbed G mu B into B also. You're right. I didn't mention that yesterday, but you're right. So okay, so yeah, it's some J tilde and B tilde. So from our viewpoint, it is just some J. If you go compare the two models, the two J's differ by some constant factor. Similarly, B also. So in one case, it's a mu B, G square, mu B square. This one, it will be G mu B. Good question. Thanks. I wanted to mention this also. I forgot. Anything else? Okay. So what we're going to do today now is that, so let us first consider the case when B is 0. That is, There is no external magnetic field. Okay, then the self-consistent equation becomes m equal to half tan hyperbolic beta what's it, j y m by 2, is it? I have to look up, sorry. Yeah, even here I forgot. That's a by 2. Does this agree now with what we had yesterday? I forgot a factor of 2 also in that. So we need to solve this equation, and so let us do the following thing. So you can see that so this is we will solve this graphically. Okay, so the idea is that you plot okay, so we plot two functions. One is the linear one, which is just, I mean, it goes to the negative side also, but I'm just, okay, this is a linear thing. And then we have to plot an hyperbolic also here. So what I'm going to do is to show you this in Mathematica instead of showing this in on my instead of drawing something. Okay, so let me just stop presenting this and present it from something else, some other window, which doesn't seem to be there at this moment, so cancel. 1 second. Okay, good. Give me a second. This is terrible. Oh, yes. Okay. So you can see something, right? So let me now. Okay, good. So you don't have to know Mathematica for all these things, but you're able to see my graphs. Okay, good. Okay. So I just want to, I've written g of x beta to be half of tan hyperbolic beta of x. But this beta is not our beta, it is beta y, you know, all those factors, right, which was beta j y over 2. Okay, so don't worry about that. So I'm plotting it for, I'll take this coefficient, which is the argument of this, make it 1. So I'm so in this thing, the orange curve is just the linear one, m equal to n. Okay, it's a 45-degree line. But the blue, okay, is the tan hyperbolic guy. And so you can see for a value of this beta tilde, let's call it, to be 1. Okay, so what we can see is that where do these two intersect? So that is the solution, right? Where do they intersect? 0. Okay, so let's see if I can make this even bigger. I don't know what I did. It made it worse, I think. No, it didn't. Next one. I don't know what happened. Now I'm not able to move it. Okay, good. So now we are going to do this for 2. Okay, you'll see that beta tilde equal to 2 is a special one. So there you can see that the slope of the blue is still the tan hyperbolic function. The slope of this tan hyperbolic agrees with this thing. One more thing I forgot to mention is that the saturation value is plus half on this side and minus half on the other side. Okay, so here you go, and you see that this is what you get. Okay, so where do they meet? They still, it's tangential, but they meet it. So now you just take it greater than 1. So I took it to be 5, I think, beta tilde being 5. And now how many intersection points do you see? 3, right? And there is a symmetry, m goes to minus m. M equal to 0 is out here. We have some m equal to plus m star and minus m star, where m star is some positive value. And now I'm here, I'm just plotting all 3 of them together. And so these red line, this one in this case is the straight line. So blue is 5. Orange is when it's exactly tangential 2, beta tilde is 2, and this is beta tilde equal to 1. Okay, so we can go here and just you can see there's a slider. Okay, so the slider goes from 1 to 5, so we can see how this goes. So as I move it to the right, you can see the slider, right? You can see the blue curve, which is the tan hyperbolic function. So we are now, you can see, close to 2, and we cross it. Slowly you see a third thing coming here. So on. Okay, at around 5, you can see that it's gotten pretty close. M star is pretty close to half. Okay, but if you go below, you can see that M star will slowly it will come down from half to slightly smaller values, and eventually it will approach 0. Okay, is this clear what I'm doing? No, that is just that's just your eye. Okay, you can check that only the tangential, only the tangents agree. So it's agreeing more than just the value. The value and the slope is agreeing, but the second derivative will not agree, because second derivative of a straight line is 0, but that will have a non-trivial second derivative. So they don't agree at second order. Good point, actually. That's a visual thing. Yeah, you're right. So come here and see. This is at 1, and it looks like they agree, but that is because your eye is so small resolution, it can't. So it's only somewhere around this thing your eye can tell. But if you zoom in, you will see that it separates. Okay? Any other questions? Okay, so let's okay, I'll stop presenting and go back to my sorry, I'm not so good at all these things, I keep messing up. Okay, so now it will come. Okay, so now you can see my slide, my tablet. Okay, so let me just define some beta tilde. I was using was beta j y upon 2. Okay, so what did we see? We saw that when beta tilde, the slope is less than so beta tilde was less than equal to less than 2. There was only one solution, m equal to 0. Okay. There were 3 solutions. We just called them 0, plus or minus m star, and as beta tilde tends to infinity, m star, what is the value of m star? Plus or minus half. M star is half. Okay. Are there any questions? That there are 3 solutions. We can see this very nicely graphically. Okay. And okay. So are there any questions and comments at this point? Okay. So, and recall that beta and beta tilde depend on inverse temperature. Okay. So recall that beta is 1 by kBt. So if you come back here, beta tilde or beta being greater than some number implies that beta temperature is lower than some critical temperature. So we'll define critical temperature to be when beta tilde, which is equal to beta jy by 2, is okay. So what does this mean? It just means that kBt 4 by, sorry, not that way, equal to jy by 4. Okay, so this Tc is called the critical temperature. So I don't need to write a second equation. So I can just take kb to the other side. Okay. So now let us try to understand the solution. So it says, so now in terms of this, so we see number 1, for T greater than Tc, the average magnetization is 0. Okay, so there is no magnetization. Is this clear? However, for T less than Tc, what we find is that M has two possible values. It's plus or minus M star, where M star is a non-trivial guy. Okay, we'll figure out what that is. Okay, and there are two solutions. Okay, so now let's interpret these solutions. What does that mean? What does the plus and minus mean? Why is it we have two solutions rather? And M equal to 0, we will explain later, is unstable. Okay, it's also a solution, it's unstable, but these are stable. We'll explain what is stable also, and ignored or thrown out. So can someone tell me what this means? Yeah, and unstable is not a solution. So what that means is that it will tend to either either plus n star or minus n star. These are the ones. Yeah, perturb we have to explain in what sense. Yeah, yes, if you perturb a little bit, it will go off to n star or n. Okay, so now the question to you is, why is it I have two values? Up and down, or spin up and spin down kind of thing. Absolutely. Okay, so these two are, so there is a degeneracy. Okay, two solutions because there is a degeneracy. B is 0, but yeah, so this is the whole point. Okay, so any one of those solutions correspond, absolutely, now that's what I'm going to correspond to non-zero magnetization. In the absence of a magnetic field. This is what you're saying, right? So what does this mean? So we have, so it's a ferromagnet. So for T implies for T less than Tc, okay, the system is a ferromagnet. And we know that if for M equal to 0, if you turn on a magnetic field, as we will see, it will become a paramagnet. So there is indeed a phase transition happening at T equal to Tc. Okay, is this conclusion clear? Hello, somebody please respond. Am I connected? Okay, good, good. Okay, so let us now try to understand what is the order. Now the next question to ask is, what is the order of the transition? So something should become singular, and what we will do is, so for this we'll let us study the behavior of n star close to Tc. So something should diverge as t goes to Tc. So we'll check, we'll see that magnetization doesn't diverge, it's bounded anyway, right? So there's no divergence from it. Okay, so it will become second order. At least we can say it's not first order. So let us okay, so near Tc we expect n star to be close to 0. We saw that graphically also, right? Slowly it starts moving away. So it's nice. It starts from, as you at 2, beta tilde equal to 2, it was still at 0. But if you just increase beta tilde to go just past 2 a little bit, it moved up. So then you got some zero value which was small. Okay. So if we do that thing, so let us look at what was our equation. It was m equal to half tan hyperbolic, okay, beta jy by 2 into m. Okay, so I'll rewrite this in a particular form. I'll take 2 to this side and write it like this. Okay. Where Tc is as defined here. Okay, jy by 4 kb or whatever. Okay, and I'm putting 2m here, and most books will actually, for us m goes plus or minus half, but if you multiply by 2m, plus or minus half becomes plus or minus 1. Okay, that's the standard textbook stuff. So I'm just writing it so that you could. So now what we do is we are going to assume this is small, and we'll expand this. So we will use the following expansion: tan hyperbolic x equal to x minus, I think it's cubed upon 3 plus order x power 5. Okay, so we'll truncate here for small x. This works for small x, we can truncate. So we'll replace this by up to cubic we will get. So we'll get your variables 2m equal to Tc upon t, 2m, okay, minus 1/3 Tc by t into 2m whole cubed. Okay, we are truncating now. That's all I'm going to do. So we have a cubic equation, and so we'll solve. So I can rewrite this, and let me pull out some 2m's, etc. So what we get is 2m into 2m whole square okay. So we can see all the 3 roots here, because so this implies the roots are, of course, 2m equals 0, okay, or now this is just a quadratic, so we can see that we will get 2m whole square equal to Okay. T upon Tc whole square into okay. So you just have to rearrange a bit. You can trust that what I have got is correct. So that you can see that this is 2m whole square. So this gives plus or okay. So now we can see this thing. So let's first consider t greater than tc. What happens to 2m? The other two roots become imaginary, right? Because it's equal to tc minus t. So for t greater than this thing, so get two imaginary roots. Okay, implies m equal to m0. M equal to 0 is the only root, only real root. Okay, is this logic clear? We knew it from other things also, from graphs. So what's happening is that okay, that they are imaginary roots, and as you come closer to tc, those imaginary roots become 0. At t equal to tc, you can see that 2m square is still exactly 0. So all three, there are the root at 0 is has multiplicity 3, exactly at t equal to tc. T less than tc, now two new roots, real roots appear. Okay, and what are they given by? It's just 2m star. No, I don't want to call that m star. 2m equal to plus or minus, you can even take m to the other side, 2 to the other side, plus or minus half into okay, or from our definition, m star was just t into okay, power half. Is this computation clear? So it's sort of it's also, we assumed m is small, and you can see if we make tc arbitrary closer to t, you can make m star as small as possible, so that the cubic approximation truncation is good. Okay, again I'll pause here. Are there some comments or questions? Where did it go? Good question. It should be there. yeah, it should be there. So there is some 3 somewhere. It goes with that, no? Wherever that thing is coming. So thank you. Okay, good. Yeah, the 3 is there. Okay. So this is good. So now we are ready to do a plot. So let's do this interesting plot, which is the on this axis we will have T, on this axis we will have magnetization, and let's just mark TC here. Okay, so what is the magnetization for T less than TC? Sorry, T greater than TC? 0. Okay, I'm just drawing it just above that, but you know it is 0. But now comes the interesting thing. How does it look here? So it's just there's a half. So if you just rotate it, it's like a parabolic, at least locally. there are two roots, so it will look like a parabola here, and then it will go and saturate somewhere. So I want to draw a wider one. Let me just draw it from here. Okay, so this behavior we have seen. So this is what we get. Okay, so there are two values. Of course, it's symmetric. So this is the magnetization versus temperature. Of course, if you want the magnetization, you have to multiply by n and all those factors. But you can see that this captures this thing. So that we see. So for t less than Tc, we get two branches. Okay, is this clear? Yeah, go ahead. Yeah, there is a degeneracy, but it's like, I mean, they have, if one of them aligns this thing, everything has to align it. So they are predominantly up or predominantly down. So it's not like that simultaneously both will occur. One of them will be picked. Okay, so we'll see that if you turn on a magnetic field, right, then the degeneracy is broken. So then you will see that it will tilt towards, so one of them will get picked up. This, okay, so if you turn on B field, it will be a different story. Okay, the degeneracy is broken, and it will pick the one which is lower energy, which is parallel, whichever direction is parallel to the B. Okay, good. Okay. So in reality, what will happen in real samples is that you will see domains. There will be locally it will do this. So there will be the one domain where everything will be up, another domain there will be this thing. So you may not see ferromagnetism because of domains cancelling each other out. This is a standard phenomenon. So you may need some, you may need to line them up, align them. So that's what you do. Okay. So there's another fact here. So that is the thing. But we also saw. Okay, another behavior, another thing, another fact was that n star was proportional to Tc minus T power half. Okay, so this is an example of something called a critical exponent. So this half, okay, so one writes it as Tc minus T power beta and says beta equal to half. Okay, so this is called a critical exponent. Okay, so this is, it says that, what does it say? As T minus Tc tends to 0 minus, right? So it's going from the negative direction. Okay, we get this critical exponent because we see beta equal to half. Okay, so there's some convention. This is called beta. You will see that means obviously there is something else called alpha, beta. I think gamma and delta also exist. Okay, so this says that our prediction here is that it will the way it will approach 0 from, if you're coming from below, is that it will go like Tc minus T power half. There are prefactors which are thing again. Okay, so this is an example. One more thing, you can see that if you take the derivative of a dm by dt, you will see that it will diverge, because it will become minus half, will become minus half. Okay, so it will diverge. So we can see that it's, I mean, some second derivative of some free energy is diverging. Okay, so it's clearly a second order phase transition. Okay, is this clear? Okay, so in this magnetic systems, we will ask how does the magnetization go to 0? Okay, and that defines this critical exponent beta equal to half. Okay, so now comes the most important comments. Okay, so the first comment is that these results, okay, these results are not dimension dependent, right? Okay, this is wrong. Not entirely correct, it's not fully wrong. Okay, so second one is the 1D Ising model. We'll see this proof at least. Ising model can be solved exactly. However, Tc equal to 0. Okay, what does this mean? If Tc is 0, we know that at t tends to 0, all systems go to their ground state, so there is no phase transition really. So in the 1D Ising model, there is no phase transition. Okay. However, again, for d equal to 2, there is an exact solution. Okay, and Tc is greater than 0, and so there is a phase. Okay, I'm just stating these things. Okay, like I said, we will see the d equal to 1 exact solution we will see, but d equal to 2 we won't. Okay, Tc is greater than 0, but of course the value of Tc and beta are different. So the exponents we get are wrong. Even the exact number, right, we wrote something, even that is not quite correct. Okay, but it doesn't matter, at least. But no exact solution is known. And this is not expected to exist. However, Monte Carlo simulations, these are computer-based simulations, show that Tc continues to be 0. Even there are other reasons also. Okay, there. So mean field theory. So implies mean field theory captures the physics correctly for t equal to 2, 3 onwards, but not. Okay, and there's another way to understand this. So this is 4, right? So fifth is now it's a theorem. Okay, so the Ising model has a discrete symmetry. In the absence of B, of course. Okay, and that's just taking all the sigma i's to minus sigma. So whatever you call up, you call it down, and you flip them, you get. You look at the energies will be the same, etc. Okay, so this is Z2 symmetry. You do it twice, you come back. Okay, so this is Z2. It's a discrete symmetry. However, for t equal to tc, sorry, t less than tc, this symmetry is broken. Broken in the sense that if you take one thing, if you take the ferromagnetic thing where everything is up, it takes you from that solution to down. But for t greater than tc, m equal to 0, so you have equal, roughly equal numbers of up and down spins. So if you flip them, you don't, m continues to be 0. Okay, symmetry is broken as m star gets mapped to minus m star under the symmetry. The two solutions get changed to each other. Okay, so now there is a theorem which I will state. Mermin-Wagner theorem. Okay, so discrete symmetries can be broken only in dimensions greater than 1. Okay, that's what it says. There's a version for continuous symmetries, and they can be broken on only dimension 2. So you can see our conclusion that we got. So that's why the mean field theory doesn't care about dimension, and it predicts this thing. But Mermin-Wagner theorem or exact computations, both of them give you the same this thing. Okay, so are there any questions about this theorem? Do you understand what one means by a broken symmetry? So there is something which is symmetry of your Hamiltonian or your Lagrangian, but is not a symmetry of the solution. So if you have symmetries, even in classical mechanics, if you have, let's just consider some discrete symmetry, even continuous symmetries are fine. It does two things. Either it could take the solution to itself, or it will take one solution to another solution. Okay, so this m star going to minus n star is taking one solution to another solution. But if you look at for t greater than 0, m equal to 0 is going to m equal to 0. It does nothing. So that symmetry is not broken. Okay, so that's what. Okay, so it's called a broken symmetry. Okay. So definition. Okay, first in classical mechanics. Okay, let G be a symmetry of the action. Okay, and and Q of t be a particular solution to the Euler-Lagrange equation. Okay, is the setup clear? So G is some group element. Let's assume it is discrete for simplicity, but it doesn't matter. So, and let's write something. Qg of t is the solution that we get when G acts on the solution. Okay, so let's okay, I'll give a so this is okay. Then if Qg of t equal to Q of t, we say that G is unbroken, or a symmetry of the solution. then we say that the symmetry is broken. Okay, it's important to note that QG is also a solution to the Euler-Lagrange equation. That won't be messed up. Okay, is this clear, this statement? Hello, are people there? Okay, so this is clear, right? So let me give you an example of a broken symmetry. Okay, so let's say that there's a free particle. Okay, and let's say Q of t is just a particle being stationary, it's not moving. Okay, so that's this thing. But let's think of G be some boost by some velocity. Okay, so is the boosted solution the same as the original one? No, it's not, right? In the boosted frame, it will be moving, right? The particle will be moving, so it's not Q equal to constant, but it's Q equal to some Vt plus some constant. Okay, so you can see that for that solution, which is a particle, stationary particle, boost is a symmetry that is spontaneously broken. But of course, we know that the equations of motion don't change, right? Under boost, Galilean invariance, Galilean boost, or whatever, right? In this case, right? Is this point clear? So that's an example of a broken symmetry. Okay, unbroken in our spin example itself, we have seen that the paramagnetic phase is unbroken symmetry, and the magnetic phase, ferromagnetic phase, is broken symmetry. Okay, so I think I will stop here. Oh, I have a few more minutes, but I think I shouldn't say more things and confuse you. So the floor is open for questions. Yeah, go ahead. With TC is 0. Yeah, so that's like nothing. It is not. No, it's approximate. We know that it gave some TC which was non-zero, and it was independent of, in fact, independent of dimension. While TC actually is dimension dependent. That's what I'm saying. It gave non-zero value of TC, right? So it's wrong in that sense. So there is no ferromagnetism in one dimension, except at exactly precisely t equal to 0. But that you expect, that everything goes to the ground state at 0 temperature. Okay, so any other questions? Okay, so let me pause the recording and stop.